Welcome back. In this lecture, we are finally going to start discussing derivatives. What are derivatives and what are they useful for? In this lecture, I'm going to make the concept of derivatives as intuitive as I possibly can for you. I will really pay a lot of attention to details and just go with the lecture, watch my videos, listen to what I'm saying, and pay attention to the examples. And I promise you, after this lecture, you will really truly understand what derivatives are. Okay, so I will start with this example. Let's say that this is a corner of your house and you have some kind of beam that is put here on the corner of the house, and then from that beam you have some kind of sphere, some kind of object that has some kind of mass. And now here you have a chain that holds the sphere in place, but then something happens and that chain breaks down. And then this sphere will start falling down, and it falls down faster and faster until it reaches the ground. So we know that the initial height of the sphere is 45 meters. So this is this distance here. And the final height of the sphere is when it reaches the ground. What would be the relationship of the height with respect to time? The function would be the height as a function of time equals the initial height, which is a constant, which is 45 meters, minus 5 times t squared, minus 5 times time squared. And it's negative because you can see from this picture that as the sphere falls down, the altitude of the sphere decreases. So the function has to decrease. So I can rewrite it like this. H is a function of t equals 45 minus 5 times t squared. Okay, so how would we find when the sphere touches the ground, in how much time the sphere would touch the ground? Well, we know that the final height would be 0 meters, right? So the final height at time final, and we can just say that the final height happens at time final, equals 0. So we can take this equation and equate it to 0. So it's 45 minus 5t squared equals 0. And this would be TF. And then we would have 5TF squared equals 45. TF squared equals 45 divided by 5 would be 9 seconds squared, because it's time squared, right? The units would be seconds squared. And then TF would be square root of 9, would be 3 seconds. So in 3 seconds, the sphere would reach the ground. Let's graph this information. So I have the axis here, and on the x-axis I have time, and on the y-axis I have the altitude of the sphere. What would be the height of the sphere at time equals 1 second? Well, we just take this function, we say altitude at time equals 1 would be 45 minus 5 times 1 squared would be 40 meters. And then at 2, the altitude at time equals 2 seconds, it would be 45 minus 5 times 2 squared would be 45 minus 20, 25 meters. Okay, let's graph it. At time equals 1, we would have 40, and at time equals 2, we would have 25. And now we can graph it like this. Okay, you can see that essentially what we are having here, we are having an upside down parabola, something like this, and we are considering this part here. The square function, or the parabolic function, would be y equals ax squared plus b, and b here would be 45, and a would be minus 5. So you can see it, 45 would be b and minus 5 would be a. In our airplane example, in our very first airplane example that we had a function that mapped distance and showed its relationship to time. We had a function like this, time here, and we had distance here, and then we had a straight line function, distance equals 800 times time. And we measured how much distance changed with respect to time by, first of all, taking this interval, new minus old, remember, delta d, new minus old, and then we divided by the delta t, which was new minus old. That's how we got the change of our function. Now, what can we do here though? Well, we could do the same thing. We can just take one interval, which would be delta h, and we could take the other interval, which would be delta time, right? And then, well, we could just write it down like this. We could say like delta h over delta time equals new minus old. So the new height would be 0 minus the old height, which would be 45. And we can divide it by the new time, which is 3, and the old time, which is 0. And you will get minus 15 meters per second. And you can graph it like this. So you would have one point here and another point here. And then you could just graph it like this. So it would be a straight line graph. Now, according to this red graph, this red straight line function, the sphere flies down at the speed of 15 meters per second. However, is it really true? Is it really what happens? Does it really fall down with 15 meters per second at the constant rate? Well, no, it's not, because the function here, the black line, it's not a straight line function. So in fact, this red line represents the average change over the interval of 3 seconds. So we take average change of the height with respect to time over the interval of 3 seconds. However, you can have as many average changes as you want, because you can take any interval you want. Let me give you an example. I could take the interval from 0 to 1. So I would have something like this. I would have this. Then my delta h over delta t would be what? It would be delta h over delta t over the time interval of 1 second from 0 to 1. It would be new minus old. So it would be 40 minus 45. And the time interval would be 1 minus 0. And it would be minus 5 meters per second. We can also take the other interval, which is 1 over 2. So here, the delta h over delta t would be 25 minus 40. 2 minus 1 would be minus 15 meters per second. And notice this is the same thing like the initial one. So here the average change corresponds. So if I draw a line here, then in fact this line would be parallel to the other straight line. So you see this straight line here is parallel to this one. Here, in this case, the straight line would be different. It would be more flat. And you can see from the numbers, the change is smaller. It's closer to 0. And of course, I can take another interval, which is this one. And here I can also take the interval delta h. And then I can divide it by delta t. So now I'm taking the interval from 2 to 3. And it would be 0 minus 25 over 3 minus 2. And it would be minus 25 meters per second, which is a greater change, and you can see it from this straight line. If I graph this straight line, it would be, let's say, more vertical. So you can see that I can take whatever interval I want. I could have an infinite amount of average change, depending on the interval that I take. Now, even though I have some information about changes of altitude with respect to time, it's not really useful, because what will I do with an average change? And in fact, the greater the interval, the less precise it is. I want precision, right? What do I want? I want complete precision. I want to know how much the altitude changes with respect to time exactly at time equals 1 second. Exactly at that time. So how would I get that? I would get that by having a straight line that is tangent to the curve and that touches the curve only at time equals 1 second. And when I say only, I really mean only. I mean that if I have this straight red line touching this black curve, and this is time equals 1, if I zoom in this part here where the graph touches the black line, then okay, I'm just gonna draw the black line here again, so it's nearly a straight line in this small section, but not quite, but it's nearly a straight line. And then I'm gonna draw this straight line here, the red one. Then I say that this straight line touches the black graph only at time equals 1 second, not at time equals at 0.9999 seconds, not at time equals 1.0001 seconds. No, only at time equals 1 second. Only at that time, the red straight line touches the black curve. Which means if I rotate this red line either in this way or in this way just a little bit, the red line would already touch the black curve in other places. So I need this perfect balance where the straight line touches the black curve only at time equals 1 second. Not here, not here, only at 1 second. And then, when I have this straight line, I just take delta h and I divide it over delta t. And that delta h over delta t that I will denote with a star is called an instantaneous change. It's called instantaneous change because it's instantaneous. It only happens at time equals 1 second. If I move just a little bit, if I go from 1 to 1.0001, then that change will change. That instantaneous change will be something else, because this line will be tilted a little bit differently, so delta H over delta T would be a little bit different. So what is my goal here? My goal is very simple. What I want is I want time as an input, and then I want to have some kind of function that takes all the possible times that I have, and then I just put the time inside the function, and what I will get that instantaneous change at that time. If time equals 1 second, I want to know what that instantaneous change is. And if time equals 2 seconds or 2.5 seconds, I want to know the instantaneous change at that time. In fact, you can see it as another function, and I could graph it like this. So I want some kind of function. So if I have time here, then I want to have some kind of function that would give me that instantaneous change. So how am I going to find that instantaneous change for each time? How am I going to find that function? Well, this is how it is done. So this is our function, time on this axis, height on this axis. We're going to take a random time, all right? Just whatever time. We don't consider a specific time, just a random time, and we're going to denote it with a t. And then we're going to take another time, and we're going to say that it's t plus delta t. Okay? That means that this interval here is delta t. So that the time has increased by delta t. Okay. So I have 1 point here, and our goal is to find the instantaneous change on this point, all right? So we want the instantaneous change at time equals t. But now we also have another point here, time equals t plus delta t. And you can see that we have some kind of average change here, so I could just graph it with a straight line. It's an average change, and in order to find the instantaneous change, I need to take this point and I need to start moving it along this parabolic line closer and closer to this original point. So if my original point is 1 and my second point is 2, I need to start moving point 2 closer and closer to point 1. And the closer I move, the straight line here would become closer and closer to that instantaneous change straight line. Okay, to that straight line where the straight line touches the graph only at time equals 1. So I need to find a mathematical way to represent those 2 points, and then I need to represent how this point moves closer and closer to point number 1. So how could I do that? Well, let's just go to our standard formula, how we find changes. Delta H over delta T equals new minus old. What would be the new height? The new height would be 45 minus 5 t plus delta t squared, right? So we're taking this time, t plus delta t squared. So that would be our new situation minus our old situation, which is 45 minus 5 time squared. So that would be our old situation, and we divided all by delta t. If we take delta t equals 0, then we should find our instantaneous change. However, we can't just put 0 inside, because then we would divide by 0 and then the equation would be undefined. So we can't find this instantaneous change through direct calculation. But that's alright, Because remember, from limits, there is another way to find things like that, things that we can't find if we have to divide something by 0. Instead of finding the instantaneous change through a direct calculation, we can find it by simply finding out what value this equation approaches as delta t approaches 0. So as delta t approaches 0, this point number 2, gets closer and closer to point 1, right? And mathematically, we would denote it like this. We would just put it inside the limit, and we would say delta t approaches 0. And the same thing here, limit as delta t approaches 0. So instead of finding the instantaneous change through a direct calculation, we just find out what this equation here approaches when delta t approaches 0. And it's another clever way to find your answer. And then we would get delta h over delta t, which is instantaneous, at time equals t. To find the limit of an equation, the first step would be to take that variable, in this case delta t, and since it approaches 0, we would just put 0 inside the equation. However, then we would divide by 0, and we can't do that. So it means that we have to find a way to get rid of that denominator. We have to take this equation and algebraically manipulate it to get rid of the denominator, so that we could put delta t equals 0 inside this equation and we wouldn't be dividing by 0. So how would we do that? Well, let's just go through the mathematics together. So remember, t plus delta t squared, it's the same like a plus b squared, and the formula for a plus b squared was a squared plus 2ab plus b squared. So this would be t squared plus 2t delta t plus delta t squared. And we would then write it down like this. Limit as delta t approaches 0 would be 45 minus 5 times t squared plus 2t delta t plus delta t squared. Now, minus, and remember, now we are opening the brackets, minus 45, minus and minus will give you plus 5t squared, and all that divided by delta t. And then again, we would have limit as delta t approaches 0, 45 5t squared minus 10 t delta t and minus 5 delta t squared minus 45 plus 5t squared divided by delta t. Now we can cancel out 45s, and you see from the derivatives later on from the rules, you will see that if you take a derivative of a constant, so if you have some kind of function y equals ax plus b and you take the derivative, then when you take a derivative of a constant, then it would become 0, and that's why it becomes 0. 45, which was our constant, our b, so our b would cancel out like this. Okay, let's continue. Limit delta t approaches 0, and by the way, these two will also cancel out, so you're only left with minus 10 t delta t, and I can also just write it down like this. I can separate them. Minus 5 delta t squared divided by delta t. Okay, so I can cancel out these, and I can cancel out this and this, and I'm left with limit as delta t approaches 0 minus 10t minus 5 delta t. And look, now we don't have a denominator anymore. We can put delta t equals 0 here, and that would make this term 0, because minus 5 times 0 would be 0. And we would be left with an answer which is minus 10t. And that would be our instantaneous change, our delta h over delta t star. And notice it's a function, it has t inside, which means I can take whatever t I want, let's say 1 or 2, and it will give me the instantaneous change at that time. So if time equals 1, then the instantaneous change would be minus 10. And if time is 2, if I say like 2 seconds, it's gonna be minus 10 times 2, so time equals 2 seconds. The change would be minus 20 meters per second, and because of the minus sign, you know that it's going down, or the altitude is decreasing. A good way to visualize this entire thing is like this. So this is our original graph that represents the original function, height and time. And then this is the derived graph of the derived function, which is minus 10t. And what it does, it maps time to the instantaneous changes of t. So as I move along t, so I go, for example, to t equals 1, and I go to this point, then this graph will give me the value which I would get if I put a straight line function that only touches this original graph at time equals 1, and that would give me the instantaneous change of that graph, that delta h over delta t at that time, at that instant. And if I go to another place, let's say at time equals 2, then this graph here would give me the delta h over delta t of that straight line that touches this original graph only at time equals 2. Only there. So this is a good way to visualize it. Essentially, you're deriving another function that represents how this original graph changes with respect to time. So now our change, unlike in the previous example or in the first example where we had a straight line function, then over there delta d over delta t would be a constant, some kind of horizontal line here, so the change would be constant. But because this is not a straight line function, you would not have a horizontal line here. You would have some kind of function that shows you how the change of this original graph changes as you progress along time. I also want to cover the notation. So our instantaneous change, which we denoted with a star, it is defined as limit as delta t approaches 0 of delta h over delta t. That's called the derivative of the function that we have here, which was 45 minus 5t squared. So this is called the derivative of this function, and we denote it either with that, with an apostrophe, or we denote it with small dh over dt. And this notation dh over dt I like this notation very much, so I can put it here. The reason why I like it is because it's a ratio. So let's say that at time equals 1, it's minus 10 times 1. It would be minus 10 meters per second. And you can see that, okay, first of all, the change is negative. If time changes, then the altitude changes in the opposite way, in a negative way. But you can also see that the change in altitude is 10 times more sensitive than the change in time. Now remember, it's not like this anymore. It's not the change of altitude with respect to time per 1 unit change of time. It's not like if time changes by 1 second, then how much will the altitude change? No, 1 second now is too much. Now we're talking about infinitesimal changes, extremely super ultra small changes. So that means that if I change my delta t just a little bit, and it's an unimaginably small number that we don't know, it's just a bit bigger than 0, but it's so small that you can't imagine it, then the change of the altitude would also be super small, but it would be 10 times bigger than delta t. And you can see it from this ratio. We're talking about infinitesimally small changes now. And these are called differentials. And you don't know how small they are. They're super small, but you know that if you change the time just a little bit, then the altitude would change 10 times more and in the negative direction. Or the other way to look at it is like this. If I start changing time, then the altitude will start changing 10 times faster. So the initial reaction of the altitude when I start changing time, the initial reaction of the altitude will be 10 times more sensitive and in the negative direction. So this was our definition for our function, and this is the formal general definition of the derivative, right? Limit as delta t approaches 0, you see that this is a new function, f t plus delta t minus the old function minus ft, and we divide it by delta t. Welcome back. So you've learned a little bit about how to take derivatives of a function. So I have a small exercise for you here. You have 3 planets, Earth, Mars, and Moon. Now gravity is the strongest on Earth, then it's weaker on Mars, and it's even weaker on Moon. So if you have some kind of, let's say, elliptical sphere or whatever object, and you drop it on Earth, then it will fall down faster. On Mars it will fall down slower, and on Moon even slower. And here you can see the position values of these spheres with respect to time. Alright, so it's a graphical function, a function represented in the graphical way. And here you can see the mathematical format of them. So here you have altitude, and here you have time. Now, as we learned before, if you take the derivative of the position function, right? You have a position function and you take a derivative of it, then what you get downward velocity. You get a downward velocity function. In other words, the function that you get will tell you how fast your altitude changes. It will describe mathematically how fast your altitude changes. So it's a downward velocity. So you will have another function here. However, if you take another derivative of this function, then you will get a third function, and the third function will describe your downward acceleration. In other words, how fast your downward velocity changes. So here's how fast your altitude changes. But if you take a derivative for the second time, then you will get a downward acceleration function. And that is your exercise. You now know how to take a derivative of a function using the limit method that we had discussed before. And your exercise is to take these three functions here and take a derivative of these functions one time. Then here you will get the downward velocity function. So time here, and downward velocity is on the y-axis. And then this function that you will get here, you need to take a derivative for the second time of this function, and then you will get a downward acceleration function. And here you have the time axis and the downward acceleration axis. So I will show you the solutions in the next video, alright? So see you there. Welcome back. This is the solution for the proposed exercise. So what was given at the beginning were these three functions that describe the object's position or the object's altitude as a function of time. And you have the mathematical functions here. And then the task was to take a derivative of this function in order to get downward velocity functions. And then once you had a function for the velocity, then you had to take another derivative of those velocity functions to get downward acceleration functions. And this is the solution here. You can see that if you take the derivative of these functions for the first time, then on Earth, the velocity function will be minus 9.8 times time. On Mars, minus 3.7 times time. And on Moon, minus 1.6 times time. And the units are meters per second because we measure altitude in meters. And so if velocity is the change of altitude with respect to time, then the units are meters per second. Now, if you take a look at these constants here, minus 9.8, minus 3.7, and minus 1.6, they're nothing but negative slopes, right? They're negative slopes. And since the objects fall fastest on Earth, it needs to have the biggest negative slope. And then on Mars, the slope is minus 3.7, and then on Moon, minus 1.6. And if you take now the second derivative of these functions, then the acceleration functions, they are constants, right? They are constant numbers as a function of time. So as you progress along time, your acceleration values don't change. So on Earth, it's minus 9.8, on Mars, minus 3.7, and on Moon, minus 1.6 meters per second squared. Because the units of acceleration, which is the change of velocity with respect to time, are meters per second squared. And it comes from this fact: meters per second per second. And so what you can see here is that since the object falls fastest on Earth, then it has the biggest negative acceleration, then Mars, and then Moon. So on Mars it's minus 3.7 meters per second squared, on Moon minus 1.6 meters per second squared. So on Earth, your body would experience a downward acceleration that is around 3 times stronger than on Mars and around 6 times stronger than on the Moon. And that is because on the Earth, the force of gravity is just much stronger than on Mars and Moon. So if you want to jump very high, then it's better if you do it on the Moon. Thank you very much. This is it for now, and I'll see you in the next lecture.